everything I'm going to talk about is joint work with Anna Belyakova, Matt Hogenkamp, and Christoph Putera. So I just want to start by recalling the Reshetikhin-derived construction of quantum invariants. So let's see. So suppose that you have some framed knot in the 3-sphere and some complex semi-simple Lie algebra G, and then what Reshetikhin-derived did is for every finite dimensional representation of quantum G, they defined some knot invariant, which is a Laurent polynomial, depending on the representation. And the representation is usually called the color. So we think of this as an invariant of the knot K colored by the representation V. And this invariant is defined in terms of morphisms in this representation category. And all these morphisms are compatible with taking sums of representation. So it follows that this invariant is additive with respect to direct sums of representation. So if you color a knot by a direct sum, you just get the sum of the invariants. Likewise, if you color your knot by a tensor product of two representations, then it's the same as just taking, let's see, the 2 cable of your knot and then coloring one component by V and the other component by W. So these Reshetikhin-derived invariants have a nice dependence on the color V. And there's sort of a slightly different perspective on this. So what you can do is you can actually extend the Reshetikhin-derived invariants to knots that are that contain several coupons. And the strands between two coupons are still labeled by representation. So here V and W are representations, and then the coupons themselves are labeled by morphisms. So here F would be a morphism from V to W, and G would be a morphism from W to V. And you're allowed to move these coupons freely along the knot. Of course, you're not allowed to move two coupons past each other, but what you're allowed to do is if two coupons touch each other, you can combine them. And also if a coupon is labeled by an identity morphism, you can just ignore it. And of course, if there's only one coupon, then there will be only one strand which just connects the top of the coupon to the bottom. And this strand will be labeled by some representation V. And so the morphisms that sits in the coupon has to be an endomorphism for that representation. So basically for each endomorphism of a representation, you get some kind of a, Reshetikhin-derived invariants. So you can think of Reshetikhin-derived invariants as invariants that don't actually depend on a representation, but that actually depend on an endomorphism of a representation. And then by construction, this invariant actually only depends on the trace class of this endomorphism. So you have this relation, labeling with the endomorphism F composed with G is the same as labeling with the endomorphism G composed with F. So here F and G can be any morphism such that the two compositions make sense. And so you can think of colors as actually being trace classes of endomorphisms. So you can either think of colors as being representations, but you can also think of them as being trace classes of endomorphisms in the representation category or in the finite dimensional representation category. So this is a slightly different perspective. And now in my talk, I want to focus on the SL2 case. So if the Lie algebra is SL2, and the representation is Vn. So here Vn is the n+1 dimensional irreducible quantum SL2 representation. So the n refers not to the dimension, but to the highest weight. So in this case, the invariant that you get is just the n-colored Jones polynomial. And it's normalized so that for the unknot, you just get quantum n. So you can think of quantum n as being kind of the quantum dimension, so to speak, of the representation Vn. Now here are some special cases. So the 0th colored Jones polynomial for the colored 0 is just always 1 because this corresponds to the trivial representation. The first colored Jones polynomial is just the Jones polynomial because it corresponds to the fundamental representation. And the second Jones polynomial is just second colored Jones polynomial is just the Jones polynomial of the 2 cable minus 1. This follows from this isomorphism. So basically V1 tensor 1 is V2 plus V0, or put otherwise in the representation ring, V2 is just the difference of this minus this, and this corresponds to this formula. And the colored Jones polynomial can, of course, also be described in terms of the temporal leap category or in terms of Jones-Wenzel projectors. So recall that the temporal leap category is a linear category. The objects are non-negative integers, and the morphisms are just formal linear combinations for flat M tangles. So by flat, I mean they have no crossings. They're embedded in some square. They have maybe M points at the bottom and M endpoints at the top. And of course, you impose this relation that the circle evaluates to Q plus Q inverse. And of course, composition is given by stacking tangles vertically on top of each other. And the point is that the temporal leap category embeds into the representation category, the finite dimensional representation category of quantum SL2. This embedding sends the integer n to the nth tensor power of the fundamental representation and basically just sends a flat tangle to its Reshetikhin-Derive invariant, or put otherwise, it sends elementary cup and cap tangles to co-evaluations and evaluations. And this embedding it's fully faithful. And well, after completing with respect to direct sums and summands, it almost becomes an equivalence. So the point is that you can use the temporal leap category to describe morphisms in this representation category. And now, if you look at the nth tensor power of the fundamental representation, it contains a unique copy of the representation Vn as a direct summand. So there's a projector that projects onto this summand. And this projector is an endomorphism in the representation category, but you can also think of it as an endomorphism in the temporal leap category, and as such, it is the nth Jones-Wenzel idempotent. And now this endomorphism, so in the trace, so the trace class of this endomorphism is the same as the trace class of the identity morphism of Vn. So to get the colored Jones polynomial, you can just take the n cable of your knot and then plug in the Jones-Wenzel projector. And this gives you a combinatorial way of defining the colored Jones polynomial, because the Jones-Wenzel projector can be described entirely within the temporal leap category without making any direct reference to the representation category. Namely, well, on the one hand, you can describe the Jones-Wenzel projector axiomatically. It just has some leading term, which is given by the n-strand identity tangles, and then you have other terms that factor through tangles with fewer strands. And it has these turnbacks properties. If you add a turnback at the top of the projector, it becomes 0. Same happens if you add a turnback at the bottom. Actually, it sort of turns out that well, if it satisfies this property and this property, it also satisfies this one, but that's less obvious. And we can also define the projector recursively. So, well, the 0th projector is the empty tangle. The first projector is the one-strand identity tangle. And in general, the nth projector is given by taking the n-1st projector and adding an extra strand, and then subtracting this term, where here this n-1 and n are again quantum integers. And this formula just corresponds to the formula that Vn minus 1 tensor Vn is isomorphic to Vn plus Vn minus 1. So basically what the formula says is this projector is the sum of these two projectors. This projector corresponds to this representation. This projector corresponds to this representation. And this one corresponds to this representation. So this is sort of the classical story. But now in my talk, I want to talk about a categorified colored Jones polynomials. So the goal of categorifying the colored Jones polynomial is to find some chain complex whose graded Euler characteristic is the colored Jones polynomial. And of course, this should not just be any chain complex. It should have some nice property. For example, it should generalize Kavanagh homology. And why would you want to categorify the colored Jones polynomial? Well, so the point is that, or maybe one reason why you want to do that is because, of course, the quantum SL2 invariants for 3 manifolds are defined in terms of colored Jones polynomials. So to categorify these 3 manifold invariants, you will probably have to know how to categorify colored Jones polynomials. And ultimately, this is also related to concordance, because categorified Witten Reshetikhin-Derive invariants should extend to 4 manifolds and to embedded surfaces in 4 manifolds. So that's sort of the motivation for why we are interested, or one motivation for why it's interesting to have categorifications of the colored Jones polynomial. And in this talk, I want to discuss two such categorifications. So one is a construction due to Kavanagh from 2003. I will say more about this construction later. And then the second construction is the Cooper-Kruskal construction. So what they did is they actually categorified the Jones-Wenzel idempotents. And there are some obvious questions. The first question is, well, how are these two constructions related? And the answer is not so obvious because they're actually different. So each, even for the unknot, for the zero-framed unknot, they yield different results. Kavanagh's construction is always finite dimensional, whereas the zero-framed unknot has a infinite dimensional Cooper-Kruskal homology. So the question is, how are they related? Another question would be, are they functorial in the knot? I won't say anything about this question today, but you can also ask, are they functorial in the representation in some sense? So do these categorifications somehow extend to some kind of a functor from the finite dimensional representation category to chain complexes? And before I said that, you can also think of colors as trace classes of endomorphism. So perhaps here we shouldn't be looking at the representation category itself, but rather at some kind of a maybe derived categorified trace of some bicategory. So I'll say more about categorified traces later. So what we did with Anna Bilyakova, Matt Hagenkamp, and Chris Putera, so we studied these questions or at least these two questions in a quantum annular setting. So what we can prove is the following. Suppose we're looking at the annular unknot, so just an essential circle in the annulus, and we look at Kavanagh and Cooper-Kruskal's complexes for the n-colored Jones polynomial of this annular unknot. And we use basically Bernotan's setting, so we regard them as complexes in the Bernotan category, but actually we want to view them as complexes in the quantum annular Bernotan category, which is some deformation of the Bernotan category. So this quantum annular Bernotan category depends on some parameter Q. And what we can show is that in this category, Kavanagh and Cooper-Kruskal's complexes become homotopy equivalent. And here we have to assume that Q is generic. So this deformation parameter is generic, where generic means that 1 minus Q to the n is invertible for all non-zero n. So in particular, this result does not hold if Q is equal to 1. So we have to deform the Bernotan category for the result to hold. And then we are currently also, we believe that we can also generalize these to arbitrary annular knots that can be obtained as closures of 1-1 tangles, but that is still work in progress. Okay, so that's the theorem that I want to talk about. And first I want to, before I come to that, I want to define Bernotan's bicategory and also the quantum annular Bernotan category that I mentioned before. Then I will recall the definition of Kavanagh and Cooper-Kruskal's categorifications of the colored Jones polynomial. Then I want to tell you why they are equivalent for the colored annular unknot. And at the end, I will talk about general projectors, and I will briefly explain how generalized projectors can be used to extend the results that hold for the unknot to arbitrary framed annular knots that are closures of 1-1 tangles. So that's the plan. So first, I want to define the Bernotan bicategory. So the Bernotan bicategory can be seen as a categorification of the temporal elite category. And it's a bicategory, so it's a weak 2 category. It has objects, 1 morphisms and 2 morphisms. The objects are just non-negative integers. Morphisms between 2 objects are just flat Mn tangles in a square. So again, by flat, I mean they have no crossings. Of course, composition of tangles given just by composing them. I guess here I draw tangles as going from left to right. So at the top of this cube, you see a tangle. So you would compose them in this direction. And then the 2 morphisms are given by linear combinations of cobordisms in the cube I cubed. And these cobordisms are allowed to carry finitely many dots. And here I'm thinking of this as being a 2 morphism going from the top to bottom. So it goes from this flat tangle to the flat tangle at the bottom. This is not so important. I mean, I could also let them go from bottom to top. But what is important is that the sides of this cobordism have to be vertical. So these sides have to be vertical. And we consider such, or one considers such surfaces or linear combinations of surfaces up to isotopy boundary and up to the usual Bernoulli relation. So for example, if there's a spherical component which doesn't contain a dot, then the entire cobordism is just 0. And now this category has some, or this pi category has some extra structure. So there's a grading on two morphisms and such surfaces, namely the degree is kind of a generalized Euler characteristic minus twice the number of dots that's in the cobordism. Also, I will usually be casual about notation, so I will implicitly assume that in this category we also allow formal direct sums of one morphism. So I'm basically looking at the additive closure of Bn, and I will also allow one morphisms to come with formal grading shifts. And it should be noted that this is a monoidal category, because if we have such pictures, we can also stack them in this direction. So you can think of it as a monoidal bicategory. You could also think of it as a tri-category with only one object. And that's not really surprising. The reason for that is just that these two morphisms are like surfaces in a cube. And if you have a cube, then you have three directions in which you can compose. So that's the Bernoulli bicategory. And now one can use this bicategory to construct the quantum annular Bernoulli category. And for that, one needs a construction known as the horizontal trace or the quantum horizontal trace. So suppose we have any bicategory which is k-linear and pre-graded. So by this, essentially, I mean that two morphism sets are graded k-modules. And now we fix some invertible element q of the ground ring, and then one can construct some category. So an ordinary one category called the quantum horizontal trace of C, and it's defined as follows. The objects in this category are just one morphisms in the original, one endomorphisms in the original bicategory C, and the morphisms between two such one morphisms are such squares. So this would be a morphism from the endomorphism F to the endomorphism G. So we have some endomorphisms at the top and the bottom, and then you have some morphisms on the sides, and then you have a two morphism that goes from this composition to this composition. And we consider linear combinations of such squares, and we also impose the relation. The relation is that one can move a two morphism that's on the left to the right, but this comes at a price. If you want the two things to be equal, then you have to rescale by some power of q, which depends on the degree of this yellow piece. So that's why your two category has to, or bicategory has to be graded. And you should think of this as follows. So you can just basically identify what this does. It basically identifies this right side of the square with the left side. If you make this identification, then you get a cylinder. So over here, we now just have one copy of P, which comes from these two copies of P, and you can think of this as the seam. So this would be like a morphism from F to G, and the composition in this category is just given by stacking such pictures on top of each other. So that's the definition of the quantum horizontal trace. And it's kind of a categorified trace it's a categorification of the notion of a trace of a category. And it comes with some extra structure. So for every object in the bicategory, you can look at the endomorphism category of the object, and there is a functor, an obvious functor, which goes from endomorphisms to the horizontal trace. This functor just sends an endomorphism to itself, but viewed as an object in the horizontal trace. And then if you have a two morphism between two endomorphisms, you just send it to this square to send it to a square which has identity seams. So that's one piece of structure. The second piece of structure is that you have in this trace, you have a morphism from F star G to G star F. So here the star denotes the horizontal composition of one morphism. So you have such a morphism, and in a way this categorifies the trace relation. So it says that in a way F star G and G star F are the same up to some morphism. And the definition of this morphism is very simple. You just look at this square, or it's a rectangle. So at the top you have one composition, at the bottom you have one composition, another composition. Now you put copies of G at the sides, and then the two morphism in the middle is just given by identity morphism. So this gives you a morphism from, I guess, F composed with G to G composed with F. We denote this morphism by theta, and it's also called a cyclicity morphism. And if you can think of this as a twist in the cylinder, so as you go from top to bottom, you twist, I guess, clockwise by 180 degrees. And now you can ask, well, can you also twist in the other direction? So can you somehow find an inverse? And of course, to kind of invert this picture, you would just have to reflect it along a horizontal line. So you'd have to reflect it as a line like this. But if you do that, then after reflecting, the G's will point in the wrong direction. So they will point upward instead of downward. But if your category has inverses, so if they're inverses of one morphisms, this is not really a problem. Now, in general, two bicategories don't have inverses of one morphisms, but you don't really need inverses. It's enough to have left duals. So if you have left duals in your category, you can define an inverse of this twist. Again, it's just given by reflecting the other diagram. The seam is now the left dual of the original seam. Then here you have the evaluation between G and its dual. Here you have the co-evaluation, and then you have some power of Q that depends on the evaluation. So you can think of this as a twist going in the opposite direction. And I claim that this is really an inverse of the cyclicity isomorphism that we saw before. To see that, you just stack, so this is theta up here, you just stack theta on top of theta of this picture, and you see what you get. And what you get is, well, such a square, but now you can take this yellow region, you can use the relation to move it to the other side. This gets rid of this factor. Now you can cancel this evaluation with this co-evaluation, and then you can straighten this diagram and you get the identity. So this shows that this composition is the identity. So the proof that theta inverses are indeed inverses is really just given by untwisting this twist in the middle. If you stack the two cylinders on top of each other and untwist what you get. And now you can do a bit more. If you have some two morphism, let's call it alpha, going from F to some other F prime, and maybe a two morphism beta going to some G prime, from G to G prime, you can still do this untwisting. And what it will do is it will reverse the order of the two morphisms that sit here, and it will also rescale by a factor depending on a factor, some power of Q depending on the degree of beta. And what this means is that you have this naturality statement. So if you look at the composition of horizontal composition of two morphisms, and you conjugate with the cyclicity isomorphisms, then this flips the two factors, and it also rescales by a power of Q. And we will use this in the following way. So later we will consider complexes in the horizontal trace, and the chain objects and differentials in these complexes will be such products. So the chain objects will look like this here, or like this here. The differentials look like this. Oh, okay. So the differentials look like this here. And now what this tells us is that that in the horizontal trace, you can get isomorphic. So if you have a complex like this, you can get an isomorphic complex in which the two factors are flipped, and in which the differentials are rescaled by a power of Q. You could think that this power of Q doesn't matter because Q is invertible, but in general, the differentials can be sums of such terms, and then the power of Q that you get over here can be different from term to term. So that's how we're going to use this naturality property later. Okay, so now you can ask, can you compute the quantum horizontal trace of bicategories? Well, in general, it may be difficult to compute the quantum horizontal trace, but at least for the Bernoulli bicategory, we can say what it is. So up to equivalence, it's just the quantum annular Bernoulli category. So what's the quantum annular Bernoulli category? Well, you look at the thickened annulus A cross I, and in this annulus, you consider such a square, which I call a membrane. And now the quantum annular Bernoulli category has the following object and morphisms. So objects are just resolutions on the annulus, so closed one manifolds, and morphisms are formal linear combinations of dotted cobordisms in the annulus. As usual, you consider them up to the Bernoulli relations, but now you also impose membrane relations, and this relation tells you what happens when you push a portion of your cobordism to the membrane. So usually when you push a portion of the cobordism through the membrane, you have to rescale, or the cobordism gets rescaled by a power of Q, depending on the degree of the cobordism. For example, a dot has degree 2. That's why you get a power of q to the minus 2. So this is the quantum annular Bernoulli category. And there's a functor from this category from the horizontal trace to this category, which just does the following. If you have such a picture, we just identify the left side with the right side, and then we get a picture in the annulus, and the membrane just corresponds to the two sides of the cube. And note, before I said that cobordisms have to be vertical on the sides, but this is not a picture in Bn itself, it's a picture in the quantum horizontal trace. And in the quantum horizontal trace, you can have non-identity morphisms on the side. So you can have these morphisms P on the side. That's why here the picture doesn't have to be vertical on the side. So this is the quantum annular Bernoulli category. Now, somewhat surprisingly, perhaps, it turns out that for generic Q, you can also identify this category with the temporal leap category. And why that? Well, the point is that taking the trace is in a way a decategorification operation. So taking the horizontal trace decategorifies this category to the temporal loop category. So taking the trace has sort of two functions. On the one hand, it kind of annularizes things, if you want to see it like that, and on the other hand, it decategorifies things. And you have equivalencies between all these categories, and you can actually describe the equivalence from TL to B and Q explicitly. What you do is, if you have the object N, you just send it to N concentric circles in the annulus, so N essential circles. If you have a flat tangle T representing a generator, you just take the product with S1, and then you get some cobordism, which represents a morphism in here. So the point now is that if you have an annular link diagram, we can form its formal Kovanov bracket, so Bernoulli's formal Kovanov bracket, and we can think of it as a complex in any one of these categories. Okay, so this is this category, and next I want to recall the definitions of the various of these two categorifications of the colored-Jones polynomial. So I first want to discuss Kovanov's construction. So Kovanov uses this formula which expresses the colored-Jones polynomial in terms of the Jones polynomials of the cables of K. And you see that in this formula, you have these binomial coefficients. And what Kovanov does is he just interprets these coefficients combinatorially. So he interprets that this coefficient as the number of K pairings of N dots, where a K pairing is just a way of selecting K disjoint pairs of neighbored dots among N dots on a line. So here we have like a 2 pairing of 7 dots. And then Kovanov constructs a graph. Here's the picture for N equals 4. The vertices are just all pairings of N dots. And then 2 vertices are connected by an arrow if you can go from one vertex to the other by unpairing 2 dots. Like you can go from here to here by unpairing these 2 dots, or from here to here by unpairing the upper dots. And next, Kovanov replaces each of these vertices by a cabling of the knot. So here we have the 2 cable because there are 2 unpaired dots. Here we would have the 4 cable because there are 4 unpaired dots. Here we have the 0 cable. And then to each edge, one can associate a canonical link cobordism, which is just basically given by an annulus pushed into 4-dimensional space, and the annulus corresponds to this pair that disappears as you go along the arrow. So then you get some commutative diagram in a category of link cobordisms. The next step is to apply Kovanov homology to this diagram. So you replace each group at each knot at the vertex by its Kovanov homology, and each cobordism by the induced map. Then you get the commutative or skew commutative diagram in a category of abelian groups. Now you add in some signs to make everything anti-commute, and then you flatten so then you have the diagram in the category of abelian groups. You flatten this diagram to a chain complex by taking direct sums of pieces that are vertically on top of each other. And the result is the n-colored Kovanov complex. And this can also be carried out for the formal Kovanov bracket, even though there are some issues that I guess don't want to discuss now. So what's Cooper-Kruskal's categorification? Well, what they did is they really categorified the Jones-Wenzel projector. So for each n, they construct some chain complex in so this is endomorphisms, the endomorphism category of the Bernoulli bicategory. So it's just objects are flat and entangles, and morphisms are are surfaces up to Bernoulli relations. So for each n, they construct, or you have such a complex, and it's characterized axiomatically by these properties. These properties just categorify the corresponding properties for the Jones-Wenzel idempotent. So particularly, you want to have a map from the n-strand identity tangle viewed as a complex in degree 0 to Pn, and you want that the cone of this map, of this chain map, is homotopic to a complex whose chain objects factors or tangles with fewer than n strands, and you want to have this turn-back property. So if you add a turn-back, you want this complex to become null homotopic. And it's easy to see that this complex is unique and that it's an idempotent up to homotopy. So if you compose, this is the composition, well, you just stack two on top of each other, then what you get is homotopic to just one of them. Cooper-Kruskal also showed that such complexes exist. And the way they proved that is they basically categorified a formula by Frenkel and Kovanev. And I won't discuss this formula, but I just want to show you some special cases. So the 0th projector is just an empty tangle viewed as a complex in degree 0. The first projector is just a one-strand identity tangle. The second projector is an infinite complex. You have a leading term, which is an identity tangle, and then you have all these other terms. And here these math BBQs denote formal grading shifts. So they're not the Qs this is not the variable Q, they denote formal grading shifts. And then this map is given by a saddle, and then the differentials are given by placing dots on various pieces. And here we take the difference of two dots. Here we take a sum. In the next term, we would again have the difference. And if you think about the decategorification of this picture, so this just decategorifies to the usual formula that the second Jones-Wenzel projector in the decategorified setting is just like given by this formula, Q plus Q inverse times this here. So the point is that the graded Euler characteristic of this piece is some power series which corresponds to this term. This term corresponds to this term. And now what we see is that this complex is essentially periodic if you ignore this term. And corresponding to this periodicity, one can construct some endomorphism, which is basically given by, well, so for example, it's given by an identity map from here to here, an identity map from here to here, and also a saddle map from here to here. And then for a higher n, you can do a similar thing. So the higher projectors also have endomorphisms of this type, but they're a bit more difficult to construct because of some technical details. So this is, I guess, Cooper-Kruskall's categorification. Let me remark that there's a different construction of a projector. I think this is due to Matt Hogenkamp. So what you do is you just define Z to be an object which is given by that formal direct sum of these elementary temporal leap tangles for all I. And then you just construct a complex by stacking such pieces on top of each other. So in degree 0, we have an n-strand identity tangle that we have one copy of Z, we have two copies stacked on top of each other. And the differentials are essentially defined in terms of alternating sums of saddles. And one can easily check that the resulting complex satisfies the turn-back property. So it is actually, and it is a categorified projector, so it's homotopy equivalent to the one constructed by Cooper-Kruskal. Okay, and now the question is, how can we show that these two constructions are equivalent for the annular unknot? Well, the idea is, so kind of as a tool to prove equivalence, we introduce something that we call a model for the colored unknot. So this is basically an axiomatic characterization of a categorification of the n-colored annular unknot. And what it is a family of chain complexes. I regard them as complexes in the temporal leap category, but you can also think of them as complexes in the quantum annular Bernoulli category, because the category is equivalent. Also, for notational reasons, I denote the object n in the temporal leap category by V tensor n. The key property that you want this complexes to satisfy, you want them to satisfy a recursion relation. So you want that Cn is homotopic to a cone of a chain map between Cn-2 and Cn-1 tensor 1. And then there are some extra conditions, which I don't want to discuss, but that's the key property. You want to have such a recursion. And now the point is that when we can prove that such models are unique, so if you have two such models, then there are homotopy equivalencies between the Cn. And the proof is actually easy. It's just induction. You have two models. You know that Cm can be expressed as a cone. You know that C prime n can be expressed by a cone. And by induction, you have homotopy equivalencies here. And now you can use these homotopy equivalencies together with some homotopy to compute, to construct homotopy equivalence between Cn and Cn prime. So models are unique. And so to prove that Kovanov's construction and Cooper-Kruskal's construction are the same for the colored annular or not, we just have to prove that they both provide models, that they both satisfy these axioms for a model that I stated before. So let me first discuss this for Kovanov's construction. So let Cn just be Kovanov's construction for the n colored unknot. We can view it as a complex in B and QA or in the temporal leap category. Of course, it's given by such a graph. So this is the example for n equals 4. And now you see that there are two types of vertices. There are vertices where the lowest dot is in a pair, like in these two vertices, the lowest dot is in a pair. And then there are the vertices where the lowest dot is not in a pair. And if the lowest dot is in a pair, then you can just ignore this pair. And then what remains generates a complex that's isomorphic to Cn minus 2. So the whole thing will be Cn. If the lowest dot is unpaired, then the corresponding vertices generate a complex that's isomorphic to Cn minus 1 tensor V, where this factor of V corresponds to the unpaired dot. So you see that the entire complex is literally a cone of a chain map from Cn minus 2 to Cn minus 1 tensor V. So in this case, Cn is not just homotopic to a cone, but it's actually isomorphic to a cone. And so Kovanov's construction yields a model. Now, what about Cooper-Kruskal's construction? Well, so now let P, bracket Pn denote the annular closure of the Cooper-Kruskal projector. And we can view this annular closure either as a complex in the quantum annular Bernoulli category or in the quantum horizontal trace of Bn. By annular closure, I just mean we identify the top endpoints with the bottom one, and we do this in the annulus. And we want to show that this yields a model. So we have to show that the closure of Pm can be written by such a cone where over here we have an extra strand. So how can we do this? Well, I first want to discuss the construction for the case where n is equal to 2. So for n equals 2, we have to show that the projector P2, the categorified projector P2, becomes homotopic to a cone if we take the annular closure. And now, what is the, here we have P0, here we have P1 with an extra strand. What is P0? Well, it's just the empty tangle in homological degree 0. P1 is just a strand, so here we just have two strands. So we have to show that this, in the annular closure, this becomes homotopic to such a cone from the empty tangle to two strands. That's what we want to show. And how can we do this? Well, remember that P2 looks like this here. And now we see that over here, we already have an identity tangle with two strands. So this corresponds to this term here. So we already have this term. So to prove that P2 has to this description, we have to show that after taking the closure, this whole term just becomes homotopic to a single copy of the empty tangle. And how can we do this? Well, we're now taking the closure. So we're in the quantum horizontal trace. So we can move this top piece to the bottom. And then we get an isomorphic complex in which these pieces become circles. So I'm just moving this to the bottom. And now when we do that, so here I'm using this naturality property of the quantum horizontal trace that I mentioned earlier. Now, when we do that, we have to keep in mind that the dots have non-zero degrees. And this means that in the differentials, we now see some powers of Q. But we're assuming that 1 plus minus Q squared is invertible. So all these factors are invertible, so we can just ignore them. And then we can deloop all of these circles. So we can use that the circle is just isomorphic in the Bernoulli category to two copies of an empty tangle. And if we apply this isomorphism consistently to each circle, then we get a complex that looks like this. So here we have identity terms. So all these complexes are just contractible summands. And so up to homotopy, we're just left with a single copy of the empty tangle. So this just becomes, in the quantum annular closure, this becomes the empty tangle. So we really get the cone of the empty tangle to this picture. So this proves the cone formula for the n equals 2 case. What did we do for general n? Well, for general n, the first step is to show that Pn has such a description. And this basically categorifies the recursion formula for the Jones-Wenzel idempotent. I don't want to say too much about this, but the differentials are again given in terms of dots and also in terms of these endomorphisms UN that I discussed earlier. So we can let these act either on the top projector or on the bottom projector. And again, what we want to show is, so we want to show that this here is a cone. And what we have to prove is, this term is already the correct term, but we have to prove that in the quantum annular closure, this tail just becomes homotopic to the closure of Pn minus 2. And to do that, we first, again, use the quantum trace property to move the top part to the bottom. Then we get a complex that looks like this. Actually, if we do this, so there's some subtleties here. If we move this part to the bottom, we actually get two Jones-Wenzel projectors on top of each other, but two Jones-Wenzel projectors on top of each other are homotopic, or categorified projectors on top of each other are homotopic to a single one. Using homological perturbation theory, we can perform these homotopies. We get a complex like this. Then we analyze these terms, and we show that these terms can be reduced to terms looking like this here, where here this star doesn't matter. And then we also be higher differentials, but they also don't matter. But the important point is that here we have identity morphisms. And now again, using homological perturbation theory, we can cancel all these identity morphisms, and we're left with a single piece of the closure of the projector n minus 2. So this just becomes in the closure, the projector n minus 2. And so we see that this projector has the desired cone description. So this is the proof. Okay, so now I mentioned homological perturbation theory several times. So what is homological perturbation theory? Well, homological perturbation theory is concerned with deformations of complexes and with understanding how homotopies extend to such deformations. So in general, we start with some chain complex, and then what we can do is we can add some, so delta is the differential of this complex, we can add some extra term to the differential, and then we get a deformed complex, which is called the twist of the original complex. So we denote this by this twist here. And now, such a twist is called one-sided if the original complex has a direct sum decomposition in subcomplexes such that all differentials in the perturbation go in one direction. So in the sense that they are strictly increasing with respect to some partial order. And we also say, so we assume that these xi are indexed by some index set I, which is a partial order, and the twist is one-sided if all terms in the perturbation strictly increase the partial order. We also says that the index set satisfies the ascending chain conditions if basically we can't have arbitrarily long ascending chains, or more precisely, if we start at any I in the index set, then we want that there's an upper bound for the length of an ascending chain starting at that I. So let me do some examples. So this would be examples of one-sided twists. So here x, y, and z are the summands of the original chain complex, and then alpha, gamma, and alpha beta are the components of the perturbation. And now what homological perturbation theory says is that if we perform homotopies on the complexes of the original chain complex, then these homotopies extend to the twists. More precisely, so if we have the sum of original chain complexes, we look at the twist of this sum, and now we replace each original complex by some homotopy complex. And then, so what the lemma says is that we can replace the original twist or the perturbation alpha by some new perturbation beta, such that the new complex is homotopic to the original one. And in particular, if all of the xi are contractible, this means that the twist is also contractible. But this only holds under some assumptions, namely, again, the twist has to be one-sided in the sense described before, and the index set, the partially ordered set, has to satisfy the ascending chain condition. And then there are some refinements of this lemma. So one can actually, there's a graded version. Basically, this ascending chain condition only has to hold within each homological degree. So let me do an example. Here we have some bicomplex. So the total complex is just supported in 2 homological degrees. Now we can think of the vertical differentials as being the original differentials and of the horizontal differentials as being the perturbation. And then this is a twist. It's one-sided because all horizontal direction, the differentials point in one direction, and it satisfies the ascending chain condition because you can't go arbitrarily far to the right. And this means that we can, so the horizontal ones are the perturbation, and this means that by homological perturbation, we can replace all these, so we can contract all the vertical differentials and we get a homotopic chain complex. And so we see that the homology of the total complex is just equal to K. On the other hand, in this example, so in this example, I interpreted the horizontal differentials as the perturbation. I could also try to interpret the vertical differentials as perturbations, but then this perturbation would not satisfy the ascending chain condition because basically we can go arbitrarily far down. So this is homological perturbation theory, and again we use this in the proof that the closure of the categorified projector is a model. Okay, now I want to say a few words about generalized projectors. So in general, if we have the fundamental, the n+1 dimensional representation of SL2 or quantum SL2, and we tensor it with the fundamental representation, then it splits into two summands, one in which the weight n is raised by one is lower by 1. Of course, if n is equal 0, then this term doesn't exist, so we just get one term. And now the idea is that we can use this relation recursively to decompose the nth tensor power of the fundamental representation into irreducible summands. And to describe this, this decomposition, I need this definition. So we look at the set epsilon consisting of sequences of pluses and minuses, and we want that this condition holds. So basically we want that if you're like at the ith position in the sequence, and you look at the portion that's to the left of the ith position, you always want that there are at least as many pluses and minuses. And we also denote by the absolute value of epsilon the sum of all terms in the sequence. Now the claim is that V1 tensor n splits into such subrepresentations that were parameterized by such sequences, and where V epsilon is isomorphic as a representation to V absolute value epsilon. And the proof is just by induction. So you assume you already have the decomposition for n. So if you now want to get the decomposition for n+1, just take the decomposition for n, tensor it with V1, then you get these summands, and now you apply this formula to each of these summands, and then each of these summands splits into either 2 terms or 1 terms, and the new terms can be labeled by either adding a plus or a minus to the sequence epsilon. So we have such a decomposition into irreducible sub-representations. And now we can study this decomposition in the temporal leap category. So we have a projector that projects onto the summand V epsilon, and in the temporal leap category, we can describe this in terms of a projector. And I think I don't want to describe exactly how I got it, but this picture, but the idea is you first start with the first, only look at the first. So this will be the projector for the sequence plus, plus, minus, plus, minus. So what you do is you start here, first only look at the first term in the sequence, this plus. Because it's a plus, you plug in a projector. Here it would not be necessary because it's just a projector for n equals 1. Now you look at the next term in the sequence, it's still a plus, so plug in another projector. But now the next term is a minus, so you add in a turn back, and you kind of continue like this. This gives you the upper half. The bottom half is just a reflection of the upper half, and then you have some coefficients. But the point now is that we can categorify this. So for each epsilon, for each of these generalized projector, we can define a generalized categorified projector. This is a chain complex in this Bernotan category, BNN. And what we can show is that the identity tangle viewed as a chain complex in degree 0 is just a twist of the direct sum of these complexes. And these complexes have all the properties that you want them to satisfy. So for example, they are orthogonal up to homotopy and they are idempotents up to homotopy. But now, do I have a few more minutes? So that's basically the thing. We can categorify this decomposition that I mentioned earlier. But now how can we deal with general knots in the analysis? And this is now work in progress. So I don't know how many details I want to give, but the idea is that Kovanov had in this paper about the functor value of tangle, he basically defined a bifunctor from part of the Bernoulli category to the category of bicategory of bimodules. This uses certain, this functor is defined in terms of certain arc rings Hm. And now you can apply this functor to this decomposition, and then this basically becomes Hn, and this becomes some twist of a sum of complexes. But if you think about it, because of how this functor is defined, so basically what Kovanov does is he starts, so you have some tangle in the Bernoulli bicategory, and what to define this functor, Kovanov closes it up in all possible ways, and then he applies some TQ of T. But the point is that most of these projectors get annihilated by turnbacks. So after doing that, most of these projectors just become contractible, or contractible is kind of the wrong word because they're not contractible as bimodules, but they're contractible as abelian groups, so become acyclic. And the point is you're only left with terms that correspond to absolute value of epsilon equal to 0. And then, well, I guess I'll skip the details, but what you get is you get a projective resolution for the ring Hn, and you can use viewed as a bimodule over itself, and you can use this to compute the quantum Hochschild homology on Hn. And then by doing some calculation in the horizontal trace that is similar to what we did before, you'll see that the higher quantum Hochschild homology of Hn vanishes. And this also means that the higher quantum Hochschild-Mitchell homology of this category vanishes, because this Bernoulli category is essentially the same as the category of, I guess, projective Hn modules. And so this is now the important point, that this homology vanishes. So we believe that we can use this to prove that if you take the quantum horizontal trace, so if you go to the quantum annular Bernoulli category, you look at chain complexes, then it becomes equivalent to some DG version of the horizontal trace of Bn. So this DG version was defined by Eugene Gorski, Paul Wehrli, and Matt Hogenkamp. And now the point is that once you have this equivalent, the last thing is that you want to do is you want to show that if you have some frame knot in your analysis, it induces some cable or some satellite functor from this DG category to itself, which basically sends the unknot to the Kovanov bracket of Kn. And now you just apply this functor to the results that we proved for the unknot, and then you get the results for general knots. And maybe to end, at the beginning of this talk, I said that colors should be viewed as trace classes of endomorphisms. And I also said that maybe in the categorified setting, so if the categorified Reshetikhin derived invariant, it should be a functor on some kind of a categorified or derived categorified trace. And this here would be an example of such a functor. So I'll stop here.